And we're back. So last class, at the end, we went over the operations of the table ADT. In order to make that time worth it, I'm not going to go in very much detail into it, just going to mention again the most important part. A table maps keys to values, student numbers to students, phone numbers to phones, URLs to IP addresses, if you want. Any pairs of data that you want to make a mapping between, a table will help you do it. We only know about 2 data structures so far, and they're both kind of bad for implementing a table. If you use an array, then search can be efficient as long as it's sorted, but then insertion takes linear time due to the need to move individual elements of the array to the side to make space for new ones. If it's unsorted, you get sort of the exact opposite trade-off. Insert is easy because you could just plop things at the end of the array, but search takes linear time because when you don't have any sorting, you have no choice but to just check every element for the thing you're looking for. And then linked list isn't that much better. If it's sorted, you have linear time complexity for everything. Recall that little table I made in a previous lecture where we found that I think either arrays are always better on paper or unsorted data structures are always better on paper. So sorted data structures certainly have their uses, but we can't really deny they slow things down due to the need to keep it sorted. If it's unsorted, you gain fast insertions, but linear time, everything else. This was the best compromise for the quiz question where we were in a situation with frequent insertions, but infrequent searches. But what if you're doing both all the time? You need something better. There are data structures, which we haven't seen yet, but will later in the course, that would allow search, insert, and delete to all be performed in logarithmic time. So that presents us with a sort of all-around alternative to the trade-offs we have here. Instead of O of n for some things, O of 1 for others, you just have logarithmic time everything. That's good, but what if you want it to be even better? We've seen examples of constant time insertions, but it comes at a cost because they basically mean you have to make the data structure unsorted and deal with slow searches. Is it possible to get search running in O of 1 time and do it without breaking the other operations? Imagine that. Doesn't matter whether you're keeping track of 5 phone numbers or 5 million. Looking up a person based on their phone number, I guess a phone number based on their name, would take the exact same amount of time, no matter what. Turns out this is possible. We could use some pretty cool techniques to get constant time, insert, search, and delete, using a data structure called a hash table. And yeah, remember what O of 1 means? It means the time to perform an operation is constant. Doesn't change with the size of the data structure whatsoever. So how the heck does this work? They sort of take advantage of the fact that arrays give you constant time random access. We already have it so accessing any given index of an array takes constant time. Looking up array square bracket 0 takes as long as accessing array square bracket 9 billion. If you have a 9 billion element array. So we already have constant time search and insertions for a table in which the keys are positive integers. And hash tables use arrays in the background to basically extend this property to any other data type. You could search the array or search the data structure by an index that is any data type, a string, a float, even any other object, and it'll present the same advantage as an array. We're going to use the letter capital N for the length of an array, and zero index the array itself. So valid array indices are 0, 1, 2, up to n minus 1. In order to bridge that gap between keys of any type and integer indices, for this example, it might be best to think of a data structure that maps names, so strings, into phone numbers. There's no easy way that we know of yet to index an array by a string. So anyway, to close that gap, we use a hash function. It's a function denoted h that takes a key k and produces an integer h of k. H of k always has to be between 0 and n minus 1 inclusive, which means that the hash function maps each key to an array index. So if we have a hash function, then we have some clarity on how the insert and search methods will work for a hash table-based implementation of a table. Insert will calculate h of k and then add the entry given at the index h of k in the array. Search k calculates h of k and then checks that index in the array. If the entry is present, then the search was successful. If it's not present, return null or throw an exception or something. Implementation decisions. The key is that h of k should require constant time to calculate. If h of k checks every element in the hash table and returns a value based on that, you're missing the point. H of k should only depend on k. We're going to talk about strings that will better apply to the phone number example and just generally more practical examples later. But for now, the simplest possible example is if keys are already integers. Then the key is already an array index, so we can just use an identity function. H of k equals k. It's easy. Insert that entry with key k at index k and search for the item with key k by accessing index k. Of course, if keys were always integers that were valid array indices, then we wouldn't be talking about hash tables. In the real world, search keys are pretty much always more complicated. Remember that I've been talking about phone numbers, names, also student numbers. I want to focus on this first point first. A student number is a positive integer. It can theoretically be used as an array index. But there's 7-digit integers that start with, for any student who's been here a reasonable amount of time, they start with either 7 or 8. So are you just gonna have a 9 million element array and just waste the first 7 million elements? Hope not. In that case, you would need to do something smarter to take that 7-digit number and then turn it into a smaller number that will be a reasonable array index. How you do that? As always, application dependent. In the case of student numbers, I would probably take advantage of the fact that all student numbers start with 7 or 8 and just like maybe chop off that first digit, the first few digits. Something like that would be a quick and easy way to shorten those numbers. There are better ways of dealing with this though. And then, of course, the cool stuff happens when your hash table's keys are not integers, because you can use strings, email addresses, authors of books, titles of any media. And in that case, you need some sort of mapping from strings to numbers. And you can imagine this extending to other data types as well, like some sort of object or any sort of object type, if used as a key in a hash table, would need a way to be associated with a specific integer. We'll talk about strings soon. There is going to be an interesting hash function that deals with strings that you'll have to use in assignment 3. But we're going to sort of build our way up to that, starting with still using numbers. This example is similar to the student number example I mentioned earlier. Say we have a catalog, like at a library or something, and each item is identified by a unique 4-digit numerical ID between 1,000 and 9,999. We're creating a table that will hold up to 200 items. So that means we need a way, so a hash function, to convert numbers from 1,000 to 9,999 to array indices from 0 to 199. Clearly, we can't use the identity function mentioned earlier. We would get an array index out of bounds exception every time. And that's assuming you're writing in a language that's generous enough to have exceptions. If this is in C, your computer's just going to break. So we need some way to compress that number range. And if you're ever dealing with compressing ranges like this, the immediate, first thing you think of should be either division or modulus, the modulo operation, written with the percent sign, or said as mod. Just a quick review of this, even though you hopefully learned it in your first year. If P and Q are positive integers, and we have P mod Q equals R, that means that R is the remainder of P divided by Q. This has an interesting property where the remainder R is contained between 0 and the divisor of the division expression, so Q. If you haven't really internalized this yet, think of this with specific numbers. If you're dividing numbers by 4, you could have a remainder of 0. If the number you're dividing by 4 is a multiple of 4, you could have a remainder of 1, 2, 3, but you can't have a remainder of 4. That 4 would just be another 1 in the result, adding 1 to the result, the remainder of a division operation is bounded above by the divisor. So we can make good use of this property by taking the modulus of the key and the array size, calculating k modulo n, and then from that operation, you get a number that is between 0 and n minus 1 inclusive. That's a valid array index. So this is our first example of a thing called a compression map. It's a function that maps integers, like this is specifically to do with integers, we'll talk about other types later, maps any integer in a big range to an integer in a small range. In this case, we're going to use a compression map that uses modulo with the array size 200 to map catalog ID numbers between 1,000 and 9,999 to array indices from 0 to 200. So this is all well and good so far, but you may have noticed that 200 is less than whatever the range of those index numbers are, 8,000 something, 8,999. There are way more potential catalog numbers than there are array indices. And by the pigeonhole principle, this means that it's possible to map two catalog ID code things into the same array index. In this case, two ID codes, 6001 and 1801, both have the same remainder when divided by 200, so 1. So these index numbers would go to the exact same array index. So that's bad. Last I checked, you can only store one item per item in an array. You can't just put two objects in the exact same memory. So we're going to have to deal with that. This is called a collision, and we're going to go over some ways in which hash tables deal with collisions. Because as the developer, you're probably not going to have any control over the keys. And that'll make it impossible to prevent collisions entirely. But we're going to have ways of making collisions occur as infrequently as possible, and also dealing with whatever collisions do happen. Personally, I think the topics of dealing with collisions when they happen are way more interesting than preventing collisions, like minimizing collisions. But it makes sense that we do have to worry about both of them. And we're going to do the boring one first. The only real way to minimize collisions is to make a smarter choice of your compression map. This will be covered later, but you might think that just making a bigger hash table can minimize or even completely prevent collisions. But it turns out that's not the case. There's some pretty neat math that basically says you will have a collision eventually, and probably sooner than you think. But it's still worth minimizing. We used a compression map, h of k equals k modulo n, but that's not the only one we could use. We could take the 4-digit code, call it ABCD, where each of those letters is one digit of the code, and then calculate A times B plus C times D. the sum of two-digit numbers has to be less than 200, because the biggest sum of two-digit numbers is 99 plus 99, which is going to be, I think, 198. So it's a valid compression map. This will always take a index ID number and then give us a valid array index. But this is really just there to illustrate the point that there are multiple possible compression maps. It's not actually a very good compression map. Values like 1234 and 3412, they hash to the same key. And in general, any pairs of numbers that have the same pairs of digits, like we see 1 and 2 here and here, and 3 and 4 here and here, they all hash to the same key. And like, making a formal mathematical definition of when this will cause collisions would probably expose even more cases. Like, I'm not quite sure how to express this succinctly, but it'll be something like any two numbers where the pairs of digits have the same sum. I don't know. Values where the first two digits are like 3 and 0 will get the same results as where the first two digits are 1 and 2. As long as the other two digits get the same number. But whatever, you get it. Patterns in the keys can result in patterns in the values of h of k. I'm going to continue repeatedly saying that like these implementation details will be driven by application requirements, like what you're actually trying to make. And what you're actually trying to make may include something to do with patterns in the keys. So what if the last digit in your index ID numbers are always 5 or 0, something like that? It's a pretty realistic scenario. Seems like all courses, or almost all courses at the U of M have that 4-digit course number, and it almost always ends in 0. I've seen 1, 2, and 6 in the wild, but it's almost always 0. So if you notice patterns in the keys that you'll be dealing with, you could take advantage of those, make hash functions that deal with them. But in this case, we're just going to talk about how they can mess you up further. So in this example of the last digit always being 5 or 0, every possible key will be divisible by 5. And this will make it so the result of that modulo operation will also be divisible by 5. And the numbers that are divisible by 5, or the available indices that are divisible by 5, are only 1/5 of all of the available indices. So you would end up actually wasting a bunch of memory you would end up wasting a bunch of memory if you use this modulo-based compression map with these specific ID numbers. So you'll have to look out for that when you're coding hash tables yourself, and make sure that you're choosing a compression map smartly to anticipate patterns in the keys. So that's it for compression maps. They are one of the two parts of a hash function. Compression maps. Oh wait, I'm getting ahead of myself. First, we have the hash code, maps a key to an integer. We haven't talked about this yet because we've only covered examples where the key already is an integer. But then the compression map maps the hash code into our desired index range. And that's what we learned about today. So next week, we're going to learn about hash codes and how to build hash tables to deal with collisions in order to sort of maximize these desirable properties for hash functions and thus hash tables to have. They should be fast to compute because hash tables are all about fast insertion and searching, and they should minimize collisions. The ideal scenario is for the hash values to be evenly distributed over the array indices, even if the keys aren't. And that's all. Assignments due tonight. I'll post the third assignment soon, and yeah, have a good weekend.
I just got my proud mark grade for the first quiz. I mean, I see like a 0 or like more stuffs.
You might have been part of the print or the scanning error that happened. Like, did you just get your?
Yeah, I just got it like today.
Oh, jeez. Because I just scanned the quizzes that had errors the first time and was planning to send them off to the markers for them to mark. So I guess if you just got told you got a 0, everyone whose quiz scanned incorrectly is going to be told they had a 0. So,
Yeah, I also got a 0.
Okay.
I was gonna submit my assignment, and then I looked. My mark was a 0.
Oh wow, that's a bad thing to see. Okay, I think I'm just gonna make an
I
announcement.
scanned the questions, like you added the numbers by the side.
Yeah, but no scores.
There's no scores
Yeah.
on it.
Okay. Yeah, so that will be resolved when the graders actually grade your stuff.
I kind of already submitted like a regrading request. Like I don't think that's gonna be necessary because it's due today. I don't want to like have that go by.
Oh yeah, I'm also gonna extend the deadline for regrading requests.
Thank you.
No problem. Yeah. Hello.
You didn't cover the way that I did my proof. I just want to know if like. So what I did was I took it and I broke it down to like its atomic statements, and
Oh,
I
like
proved the
the-
atomic statements true.
Like the terms.
Yeah, I proved that they were in little o.
Oh, okay.
Is that cool? And
Yeah.
then because that's the simplest form, I said like I've broken it down to its atomic statements, and I proved them true. Hence, statement S is true.
Yeah.
And will I lose marks for that? I feel like,
Yeah. So you used or something like
I
steps
did it
2
like
and 3.
backwards. I did it.
So showing that.
So first I
each
said,
thing is in,
suppose
or n
this.
cubed is in big omega.
Yeah.
Each thing.
And then I
Oh,
broke
okay.
them down using the rules
Mhm.
until I used I used 1 and or 2 and 3 to prove that it's true.
Oh, okay. So I think
Or
that,
wait, sorry, I used 1.2 and 1.3 to show that it's true. Yeah.
Yeah, I think that would lose a bit of credit because while we do have rules for showing that a sum is in some asymptotic group of a function, we don't have any rules for showing that a function is in an asymptotic group of a sum.
I see.
So that reversal with 3.3 was necessary.
That's what I did. I took them out, so it was little o.
Yeah.
Yeah, and then this and that.
Yeah, actually, if you
We could
Oh.
probably find it.
Yeah. Do you remember roughly when you handed yours in? Because this will be
Maybe-
in chronological order.
Maybe about here. It is chronological, yeah. Also, or do you wanna like ask
Oh,
me-
no, you can go ahead.
Okay, wait, let's do a binary search here.
Heck yeah. Wait, no, they're not sorted.
Do you wanna look through this?
Sure.
Oh yeah.
That's another kind of binary search.
Nicola. No, okay.
Oh, found it.
Nice. So back. So like this, is this enough?
Well, let's see. Okay, so you got the reversal showing that each term is in
Wait, why did I
open
write
key.
4? I wasn't thinking, but
Okay, so I think this would still lose like a mark or half a mark
Mhm.
because it doesn't use the sum rule.
oh wait, for no 4.3. By 4.3 we see this.
Oh, okay.
I just use
Oh.
it backwards because if this is true in the implication, then this must be true.
Yeah. Hold on.
Wait. Oh no. If this is true, that must be true. Never mind. Oh, I'm losing a mark there. Okay.
Yeah.
Wait, and then for the linked list stuff, I didn't. Okay, I reviewed it on, but I did not say it needs to be. I didn't specify sorted or unsorted. I thought it was just implied that you just kind of append to the end.
Oh, okay. Then I guess that would implicitly say you chose an unsorted
Yeah.
data structure.
Since because I feel like if you're not saying it's sorted,
Yeah. Sure. Well, yeah, that's the classic. I can't predict the marker's behavior because they're a different person.
yeah.
But like, I think that if I were marking that, I would sort of pick up on that you meant
Mhm.
unsorted if you're talking about inserting at the end,
Okay.
and then you'd be fine.
All right. Thank you.
No problem. You too.
My question is going to be a weird one, but is it okay? Like, I think I wrote commas in the stack and the Q1.
Oh,
is it okay if I just
absolutely,
rub them?
yeah.
Thank you, please. I would have lost like half my marks in this. Do you want to help me do the research?
Like, I
It's-
think I can understand what your
Yeah. So
thing looked
instead
like.
of yeah,
4
I just
comma 2.
yeah, I just wrote 15 comma 2. So
Yeah.
I just want to rub the commas.
That's no like.
That should be okay.
The commas won't lose you marks.
Oh, it wouldn't lose
and,
me. Okay.
And in any case, you wouldn't be allowed to modify your
Yeah,
quiz
that's the
after
thing.
handing
I
it in.
was just hoping. So yeah, I wouldn't lose marks.
You won't lose marks.
Okay, thank you.
No problem.
Also, I had another question. So how I did my last question was I assumed and I was hoping for a contradiction.
Oh, okay.
Yeah. So would that work as well?
If you pull it off,
I mean, I
Right.
think I did it rightly, but I'm not sure. Like, yeah, I can just show it to you. So it's basically similar. So I just did this. I used 3.3 first, and I say that we assume that this is true because we have this, and we have to assume that this is true, right? And then we
sorry, are
hope
you pointing at 2.3 or 3.3?
3.3.
Okay.
So I assume this is true
Yeah.
by 3.3, and then I was hoping for a contradiction that this will not be true, that f will not belong to small o g.
Oh,
And then
okay.
I go on and on, like I do this, and then
Ah.
I add them up, which means that my assumption is still true. And then at the end I say that by 4.3, by 3.3, that my assumption still stands true, and that would still mean that g belongs to small omega f.
Yeah, that's cool.
Would that
Like,
work?
that's definitely a valid proof structure. I'm just not sure if it can be done with these statements.
Oh yeah, I
So-
don't think so. It can be done, but yeah, I feel like if the way I wrote it out, I think it would be like easy for the marker to know what's happening in my proof.
Okay.
But yeah,
So, let's see. You're basically showing that this is not in little of
yeah,
that.
I would have to show that.
by-
Yeah.
Um,
So what f small o means is like this is less than this, right?
Yeah.
That's what it would mean. So I'd
Mhm.
have to show that
so then you'd sort
according
of.
to the proof, it will never be like that because it will
Yeah.
always be in the small o.
Oh, okay.
The log will belong to small o, and
Yeah.
and
In
square.
that case, you might have done an unnecessary contradiction because, like,
yeah.
you assumed the negation and then found a contradiction with the negation.
Oh no, I did
by
not negate it.
proving- Oh wait.
I would have to find a
Oh, yeah.
contradiction, right?
Um,
Because I've made an assumption that that is true.
This is hurting my brain to think about. I want to just look for
Yeah.
yours. What's your name?
Brijesh.
Oh, found you.
Yeah. So you see over here. We hope for a contradiction to prove that n3 does not belong to small omega n. And then I write this, and then I go on, and I say that since our assumption is true, therefore again by 3.3.
Oh, okay.
Because it kind of makes sense. Like
Mhm.
if this was true, then one of these would not work, right?
Yeah. So like steps 2 through 5
Yeah.
make perfect sense, and I think you'll get full marks from there. But
Step
the
1.
contradiction seems weird. Like assume by 3.3, it's not clear what you're assuming using 3.3.
We hope for a contradiction
Yeah.
to prove this, but and then I write this.
And
Because
then.
by 3.3, I'll have to exchange. I have to reverse it, right?
Mhm.
And then I write this.
Yeah.
It-
It just still seems weird. Like
Yeah.
you're saying that you're proving the negation, which is definitely not what you're supposed to do.
We now hope for a contradiction. Like I'm hoping that there is a contradiction to prove this.
Oh, like
Yeah.
you're hoping that you
I'm
find
expecting,
a
like,
contradiction
yes.
on the way to proving this?
Yes.
Oh, okay.
But
so,
since I did not find anything that contradicts this, a contradiction that proves this, so I feel like this is going to be true as well.
Okay.
As well.
yeah, so like I said, I think your entire proof, at least starting from step 2, is logically
Yeah.
perfect. It's just that the structure with the contradiction is unnecessary. Basically just did a direct proof in the remaining steps.
Yeah.
So I don't think the marker will penalize you for that. I might take off half a mark for weird structure.
Oh yeah, I don't mind that. Half a mark is okay. I thought I was
Cool.
gonna lose like a buck. But yeah, about this one, I was talking about this, like this. So just put
Oh yeah, that's completely
commas
fine.
in the middle somewhere.
Yeah.
Not every
Like,
yeah, just,
I
yeah.
think in later lectures where we keep using stacks and queues,
there would be.
I would put commas there. So like, it's fine. The marker will understand you.
And you said you have to write there would be an exception. I just wrote an
Oh.
exception.
Okay,
Would
yeah,
that
that's
work?
fine. That's
that
cool.
would work, yeah. Because there was no, I thought there was no space, so I was about to write stack empty exception,
Yeah.
but yeah.
The marker might penalize you for that because the answer key says
null.
null. But I think that your thought process is correct. So if you get penalized for that, just let me know.
Yeah, I actually pulled up my notes from my code notes from 1020
Oh,
because
yeah?
we had done stack there, and I literally did the same thing,
Okay.
like just to see while I was going through the notes, right?
Yeah.
And then it showed me an exception, so I was always write an exception.
Yeah.
But yeah, do you have office hours today?
Yeah.
Okay, thank you.
No problem. Hello.
Just gonna ask a quick question, or should I come back into office?
Um,
What do you think is better?
I prefer office hours
Okay,
actually.
I'll be back
Yeah.
in.